Thanks very much, Mehdi, and thank you, folks. It's getting late in the day here, so thank you for coming to this one. I'm going to talk about placing Spark and Hadoop in general on VMware vSphere. And the first thing people say to us always is, isn't this going to slow things down if you put things on virtual machines? But if you think about the public cloud, whether it be Amazon or Google or Azure or any other public cloud, most of them are running on virtual machines today. So doing Spark on virtual machines is not a strange thing to do. It's a very natural thing to do. We're all doing it on public cloud today. My talk is largely going to be about vSphere running in-house on in-house servers. But in the next couple of months, you're going to see VMware vSphere on AWS equipment, running on bare metal servers that are in AWS data centers. So you're going to be able to use vSphere itself in the same way that you would use AWS today. So this talk also applies to that environment, both public and private cloud. And why virtualize Spark? Well, why not virtualize Spark is the question I pose back to folks who say this. But just to give you some answers to it, really, the people who manage IT in your companies, or even when you go public cloud, want to provide Spark clusters as a service on demand to its end users. And we do that by cloning virtual machines. In my own work, I put Spark jar file and set the Spark home directory in a single virtual machine, and then I clone that virtual machine over and over again. And I've had lots of conversations on our booth downstairs about why use virtual machines, why not use containers? Are containers and virtual machines competing with each other? And the answer is they're not competing with each other. Containers are a packaging mechanism that work fine, and we support them. We even have products that integrate with Docker. And virtual machines provide other functionality to do with isolation of performance, isolation of security concerns. Data science team 1 wants to be separated from data science team 2, the best way to do that is on virtual machines. And that's what clusters as a service is. So enterprises have development, testing, pre-production, staging, and production clusters that are all necessarily separated from each other. They're not all in one gigantic cluster. And they need different versions of Spark. We've been through how many versions of Spark now? I'm on Spark 1.6, you're on Spark 2.1, somebody else is on Spark 2.2. It's difficult to run different versions of Spark in the same cluster. So the way you do this is you put each version into a cluster of its own, and you can have all of them running on the same hardware at the same time if you want to. So no longer do enterprises want to dedicate a specific set of hardware, 15 or 20 physical machines, to just one purpose, one Spark cluster, one Hadoop cluster. And the way to get away from that dedicated hardware that you may have in your data center today is to virtualize it. So those are the reasons. You can come and argue with me afterwards about whether you believe these reasons or not, but we have many, many of our customers, and VMware has well over 300,000 customers coming to us and saying, help me with virtualization of Hadoop and virtualization of Spark. And we've done lots of research and testing and performance testing, and we can show you that if you organize your virtual machines to be very compliant with the NUMA boundaries of your hardware, then you can actually get 10% better performance out of virtualized Spark than you would out of physical Spark. And we can explain that to you later on. So the archetypal architecture of a yarn system looks like this. Workers and masters. When virtualized, it looks like that. It's every role that you would consider in a physical world now in a red box, i.e. a virtual machine. There's not a lot to it other than that. You construct a virtual machine using VMware vCenter, which is our management environment, and from there onwards, the virtual machine looks like exactly like a hardware machine. It's got CPUs called virtual CPUs. It's got memory called virtual memory. It's got disks called virtual disk. But essentially, it's just like a physical host. As far as Spark is concerned, or Hadoop in general is concerned, it is a physical host, although it's a virtual machine in our terminology. And if we look at the core Spark architecture, then we have, and I'm looking at Spark standalone here outside of the yarn context, It works in both contexts on VMware, by the way. We have the driver on the top, and we have workers. Inside each worker, we have an executor, which at the core of every executor is a JVM process. And to virtualize that, you simply put all of the units into virtual machines. You don't change the architecture at all because you're virtualizing. So you may say to me, if I have multiple data nodes running in different virtual machines on the same server, and I were to lose that server, would I lose 2 copies? And VMware takes care of replicas being across different physical servers. We have technology for doing that. So virtualizing Hadoop Yarn and virtualizing Spark does not change the architecture in any way. It's simply virtual machines instead of physical hosts. Now we look at Spark running on Yarn, and here again we have Resource Manager and Name Node, and you'll notice I have multiple data nodes, so this is an HDFS environment at the bottom. We can work with local storage as well, by the way. There's nothing wrong with using VMware with direct attached storage, as you see here. You may have heard about VMware using shared storage for particular purposes that we use shared storage for, such as vMotion, moving virtual machines around. In this case, these virtual machines are not going to move around. They're going to stay on the servers that they were built on, specifically because I want it that way. And data locality is achieved by using local storage, and data safety is achieved by ensuring that all 3 replicas of an HDFS block go to different servers. We ensure that for you. So executors and drivers work exactly the same way. Containers work exactly the same way. The architecture is not changed in the slightest bit because this is all virtualized. So now some reference architectures, and I'm going to dazzle you with the next picture here. This is 2 virtual machines running on a physical host, which I've described as the virtualization host at the bottom. These 2 virtual machines contain the node manager and data node that's classic in Yarn or classic in Hadoop. They might contain an executor, for example, in Spark as well. And you'll notice here that they're writing to directories which are supported by XFS or ext4, whatever file system you choose to use. And those relate to virtual disks, which are at the bottom of the upper boxes. The upper boxes are virtual machines. The lower box is a physical machine. And this is just 2 virtual machines running on a server for illustration purposes. This could be 4 virtual machines. It could be 10 virtual machines. But the point about this is all of the local storage at the bottom of the diagram, which represents either local flash or local spinning disk or local NVMe, is entirely dedicated to its own virtual machine. There is no interference between these virtual machines as far as I/O is concerned. So one of the concerns that people frequently express to us is if I put 2 virtual machines on the same box, don't I get interference immediately? Don't I get I/O bottlenecks because they're interfering with each other? Well, this is the way to get around that. You take a subset of the storage devices, the disks, on each server, which is represented by the host server, and you dedicate it completely to one VM. That virtual machine is never going to move anywhere. It's going to stay where it is. If it happens to die, we resurrect it elsewhere. So a bunch of features that were in traditional vSphere might be turned off here, like the motion, the movement of virtual machines from one server to another might be turned off here because we've decided we know the best place to place these virtual machines, and we don't want them to be put anywhere other than that's where we chose to put them. Now downstairs in the demo hall, I'm running 3 executor processes on each of these virtual machines. I'm running that across 16 virtual machines, and so I have 48 executors, 2 cores, which are virtual CPUs in our terminology per executor, and I can train a model in logistic regression in about 40 seconds over 3/4 of a terabyte of data. So 1 million examples, 10,000 features, 3/4 of a terabyte of data takes about 40 minutes to train that model using stochastic gradient descent. So we work with Cloudera closely on virtualizing Hadoop and virtualizing Spark, and we have a reference architecture with Cloudera and the reference architecture with Hortonworks on that. You can get hold of that from me or from vmware.com/big-data. You can find that there. And just to prove my point earlier on performance, we did about a year and a half's work on performance of Spark on vSphere using two analytic programs from MLlib. They were support vector machines and logistic regression, and those are published in a white paper that you can get from us. It's called Best Practices for Performance of Big Data on vSphere 6, and you can get that at our website. And here are the key results. When support vector machine, we use 10 ESXi hosts. That's 10 physical servers to compare the bare metal performance, the non-virtual performance, against the virtual. The virtual performance is in red. The physical performance is in green. As you can see, we're about 10% better there in the final results. In the red case, in the ESX, which is VMware's hypervisor case, we were running 4 virtual machines per server, typically. So 4 instances of a worker per server. That's one benchmark that's already published, and this was executed across 0.5 terabyte, 1 terabyte, and 1.5 terabytes. That was done about a year ago. Today, we're executing against 3, 6, and 10 terabytes with the same workload using NVMe as storage, and we're getting roughly the same results, about 10% gain over physical. In logistic regression, we did about the same, maybe 1 or 2% worse than physical. And that was largely due to memory constraints. We fixed those, and we're now coming in slightly better than physical. Here again, the red is the VMware number. The green is the physical number. This is published in a white paper, as I said, that you can get from us. And you can see here for logistic regression, over 0.5 terabyte, 1 terabyte, 1.5 terabyte, we're about equal to physical performance with exactly the same hardware, direct attached storage, virtualized versus bare metal. So support vector machines stayed in memory about 10% faster when virtualized than on bare metal. And of course, staying in memory is the key thing for all of these Spark workloads. When you start spilling to disk, you're going to hit a performance issue whether you are physical or virtual. We don't change that. Logistic regression, written to disk, at the larger data set sizes, a slight disadvantage compared to bare metal. As I said, this result is about a year old. We've improved this result. We'll be talking about this at VMworld, which is our big conference coming up in Las Vegas in August. We'll be talking about this particular workload. Part of the data set was cached to disk, but the larger memory of bare metal Spark executors helped. We had more memory when we didn't virtualize because of the nature of overheads there. By the way, the cardinal rule when you virtualize or put things into virtual machines is design your virtual machines so that their memory fits within a NUMA boundary, non-uniform memory architecture boundary. Once you do that, you'll get the performance gains that we show here in this support vector machine case. So both workloads show linear scaling from 5 to 10 hosts. We've increased that to 20 and 40 hosts and got the same linear performance, which you'll be getting from us this year. When I spoke about NUMA, what I meant was configure your virtual machines, which you see in the colored boxes here, to have appropriate amount of memory such that it'll fit into a NUMA node of 512 gigs in this case. This is just an example. And you notice that I have 1 terabyte of RAM on my server. I take a little bit of RAM away for vSphere to use, and I divide the rest by the number of sockets. That gives me my NUMA size, and I configure my virtual machines to fit precisely within those NUMA boundaries. And I'll get the best performance that way. This, by the way, is very difficult to predict in the public cloud. You know, who knows what architecture you're running on in public cloud? In private cloud, you have complete control over this. In VMware Cloud on AWS, you will have control over this as well. I have 1 minute left, so I have 1 minute for conclusions. So Spark workloads work very well on VMware vSphere. We can show it to you downstairs in the demo area. I'm running on 16 and 20 virtual machine collections. I'm running against 1 terabyte and higher of input data. And we have best practice guidelines that help you. If you need to know more, go to vmware.com/big-data. vmware.com/big-data. We have design patterns like separating the compute from the storage, You can store your storage elsewhere in Isilon type storage or in shared storage, or you can use direct attached storage as well. And thank you very much for your time. Thank you.